Hello. Today we'll be presenting on speech synthesis. In this presentation, we will be going over the following. What is speech synthesis? The history of speech synthesis, the use cases of speech synthesis, methods, platforms, challenges, and the future of speech synthesis. We will begin by going over what is speech synthesis. Speech synthesis can be defined as simply as the artificial production of human speech. Specific computer systems can be utilized for this purpose. They are often called speech computers or speech synthesizers. Speech synthesis has a variety of uses which we will touch on later. These implementations of speech synthesis range from hardware to software applications. When speech synthesis originates from text, this is called text-to-speech. Text-to-speech is not the only form of speech synthesis, as phonetic representations can also be used for this purpose. Uses can also help those with any impairments or disabilities that may affect their vision or their reading abilities. These systems are often accessible as they have been on computers that have been made available to the public since the 1990s. But there are many drawbacks to current speech synthesis systems. These will also be discussed later. Oftentimes, it is considered that the more human-sounding a synthesis is, it is regarded as a system of higher quality. The systems that complete text-to-speech synthesis are composed of two parts: the front end and the back end. The front end portion begins by converting text into written words if any numbers, symbols, or abbreviations are present within the text. This is considered to be the pre-processing stage. It consists of tokenization or text normalization. Phonetic transcriptions are then assigned to words, and the text is split into prosodic units. These can include phrases, clauses, or sentences. The latter process can be called text-to-phoneme or grapheme-to-phoneme conversion. The transcriptions and prosody details are the output of the front end. The synthesizer, or back end, converts the representation into sound. This can consist of the computation of optimal target prosody, which is then the output as speech. The speech created through the concatenation of recorded sounds from a database. Databases range in contents. Some with larger output ranges contain phones or diphones, but in turn can lack in clarity. If entire words are stored within the database, output will be of a higher clarity. This will later be discussed. We are now moving on to the history of speech synthesis. Speech synthesis originates prior to the development of electric processes. A legend of brazen heads exists, and it is attributed to Pope Sylvester II, Albertus Magnus, and Roger Bacon. In 1779, Christian Gottlieb Krassenstein built a model of a vocal tract that was able to produce vowel sounds. In a 1791 paper, Wolfgang von Kempelen described a creation that utilized bellows and paper to make sounds of speech. Von Kempelen's creation was later used as a muse for Charles Wheatstone's 1837 creation. In 1846, Joseph Faber displayed euphonia. Later, in 1923, Paget resurrected the design of Charles Wheatstone. In the 1930s, the vocoder was produced by Bell Labs. Leading into 1950, Haskins Laboratories created the pattern playback. The pattern playback converted visuals of patterns into sound. Later, Alvin Lieberman utilized this to discover acoustic cues for the perception of phonetic segments. Computer-based speech synthesis began in the 1950s. In 1968, Noriko Umeda created the first text-to-speech system that operated based in English. Prior to this, in 1961, John Larry Kelly Jr. and Louis Gersman used an IBM 704 in order to synthesize speech. This machine sang Daisy Bell and was accompanied by music. It was then later used in the movie 2001: A Space Odyssey. At this point, research continues to find mechanical speech synthesizers, despite electronic speech synthesizers being so successful. Linear predictive coding, a type of speech coding, started to be developed at Nagoya University with Nippon Telegraph and Telephone in 1966. In the 1970s, Bell Labs furthered research on this. LPC became the basis for Texas Instruments speech chips. In 1975, Itakura, developer of LPC, developed line spectral pairs for high compression speech coding. By the 1990s, it was adopted by nearly all international speech coding standards. In 1975, Musa became one of the first speech synthesis systems. Later, in the 1980s and the 1990s, the DEC-TALK systems rose to dominance. These were the work of Bell Labs and MIT. The work of Bell Labs is one of the first systems that was multilingual language independent systems, made possible by natural language processing methods. Voices began sounding female when Ann Sertle at AT&T Bell Laboratories created a female voice. As of 2005, it has been predicted that systems for speech synthesis will eventually become cheaper due to the price-performance ratio.
My name is Riddhi Persana, and I'm going to be discussing the next section of the presentation. I'm going to go over the use cases of speech synthesis, the methods used, and the platforms that are used for speech synthesis. The first topic that I'm going to go over are the use cases of speech synthesis. Speech synthesis is the artificial production of human speech and is widely used for various applications, from assistive technology to gaming and also entertainment. Speech synthesis can be found in a multitude of applications. However, it is important to note that this technology was originally designed to help people with disabilities, particularly visually impaired, in their daily lives. Before synthesized speech, specific audiobooks were used where the content of the book was read into audio tape. The spoken copy of any large book took several months and was very expensive. So the speech synthesis methods was a great solution for this problem. Synthesized speech can be used also in many educational situations. A computer with speech synthesizer can teach all year round. It can be programmed for special tasks like spelling and pronunciation, teaching for different languages, and also can be used with interactive educational applications. Some of the modern-day applications of speech synthesis are used by us in our day-to-day lives. The first one is Siri. Siri is a personal assistant developed by Apple that communicates using speech synthesis. The speech synthesis algorithm in Siri uses deep learning models. This results in the voices that are more natural, smoother, and allow Siri's personality to shine through. The Hey Siri feature allows users to invoke Siri hands-free. A very small speech recognizer runs all the time and listens for just those two words. When it detects Hey Siri, the rest of Siri parses the following speech as a command or query. The microphone in an iPhone or Apple Watch turns the user's voice into a stream of instantaneous waveform samples. A spectrum analysis stage converts those waveform sample stream to a sequence of frames. About 20 of those frames at a time are fed to the acoustic model, a deep neural network model, which converts each of these acoustic patterns into a probability distribution over a set of speech sound classes, which are used in the Hey Siri phrase. The second widely known application of speech synthesis is Alexa. Developed by Amazon, its functioning consists of recording the user's words and sending it to Amazon servers to be analyzed more efficiently. This requires a lot of computational power. Amazon then breaks down the user's orders into individual sounds and consults a database containing various words' pronunciations to find which words most closely correspond to the combination of individual words. It then identifies important words to make sense of the task and carries out corresponding functions. Amazon's servers send the information back to the user's device and Alexa may speak. If Alexa needs to say anything back, it would go through the same process, but in reverse order. The next application of speech synthesis is Google Assistant. Google Cloud Text-to-Speech enables developers to synthesize natural-sounding speech with more than 100 voices available in multiple languages and variants. It applies DeepMind's groundbreaking research in WaveNet and Google's powerful neural networks to deliver the highest fidelity possible. Many Google products, example, the Google Assistant, Search Maps, come with inbuilt high-quality text-to-speech synthesis that produces natural-sounding speech. Google's Cloud-to-Text speech function can be used in a variety of ways. For example, it is used to power voice response systems for call centers and enabling real-time natural language conversations. It is also used to enable IoT devices to talk back to the user. And it can be further used to convert text-based media into a spoken format. The neural network used in Google Assistant comprises of training data that is fed into the neural network. The more training data that is fed into the neural network, the more accurate the results are. And it is also better if this training data is diverse. There exist numerous applications of speech synthesis that we knowingly or unknowingly use in our day-to-day lives, which has facilitated the ease and also the speed of performing various tasks. The next topic that I'm going to discuss is methods used for speech synthesis. The first one is articulatory synthesis. Articulatory synthesis tries to model the human vocal organs as perfectly as possible, so it is potentially the most satisfying method to produce high-quality synthetic speech. On the other hand, it is also one of the most difficult methods to implement, and the computational load is also considerably higher than with other common methods. Thus, it has received less attention than other synthesis methods and has not yet achieved the same level of success. The articulatory synthesis is quite rarely used in present systems, but since the analysis methods are developing fast and the computational resources are increasing rapidly, it might be a potential synthesis method in the future. The second one is Foreman synthesis. A Foreman synthesizer is a source filter model in which the source models the glottal pulse train and the filter models the Foreman resonances of the vocal tract. Formants are frequency peaks in the spectrum which have a high degree of energy. At least 3 formants are generally required to produce intangible speech and up to 5 formants to produce high-quality speech. Since Foreman synthesis provides infinite number of sound, this method is more flexible than other speech synthesis. The third one is concatenative synthesis. As the name suggests, concatenative speech synthesis is based on the concatenation of pre-recorded speech segments in order to create intangible, high-quality speech. The advantage of this approach is extremely high naturalness of the produced speech, as long as the system is well-designed and suitable speech data is available for its development. The drawback is limited flexibility, as all the used speech segments have to be pre-recorded, limiting the choice of speaker voices or other modifications to the verbal expression, and it also requires more memory capability than others. The fourth method, and the most widely used method, is parametric synthesis. Statistical parametric synthesis can be described as generating the average of some sets of similarly sounding speech segments. One of the techniques in statistical parametric speech synthesis uses hidden Markov model based generation synthesis, which is recently shown to be very effective in generating acceptable speech synthesis and can also be found in Siri. This method offers a wide range of techniques to improve spoken output without having to record speech, which makes it a widely used technique. The next topic that I'm going to discuss is the platforms that are used. The first one is Amazon Polly. Amazon Polly is a service that turns text into lifelike speech using deep learning techniques. In order to do this, consistently fast response times are required. When the user sends text to Amazon Polly's API, it returns the audio to the user's application as a stream so the user can play the voices immediately. Hence, it is quick and returns the voices in real time to the user, which makes it a widely used platform for speech synthesis. The next one is Azure Text-to-Speech API. The text-to-speech feature of the speech service on Azure has been upgraded to the Neural Text-to-Speech engine. This engine uses deep neural networks which allow real-time speech synthesis using the Speech SDK or REST API to convert text to speech. It also allows asynchronous synthesis of long audio using the Long Audio API to asynchronously synthesize text-to-speech files that are longer than 10 minutes. And further, it has pre-built neural voices which allow to make interactions with chatbots and voice assistants more natural and engaging. They also convert digital text such as ebooks into audiobooks and enhance in-car navigation systems. The third platform is IBM Watson Text-to-Speech. It consists of an API cloud service that enables the user to convert written text into natural-sounding audio in a variety of languages and voices within an existing application or within Watson Assistant. It allows the user to design their own unique branded neural voice, and they can also personalize the voice quality and control the tone of the voice. The last platform is Murf.ai. Murf Studio comes with a free grammar and punctuation assistant which identifies any grammar, spelling errors, or punctuation improvements in the text and provides suggestions on how to improve the script for a better quality voiceover. One of the coolest features in the Murf Studio is emphasis. The user can specify which parts of a sentence they want the voice to put more or less emphasis so that the voice can sound more interesting.
Hi, I'm Vinitha, and today I will be discussing the challenges involved with speech synthesis. So an overview of these challenges include pitch contour, pronunciation, prosody, intent, and database size. So first, to go into pitch contour and pronunciation. Pitch contour is the curve or function that maps out the pitch given a period of time. And this relates to a frequency function, which maps out the frequency at one point in time to a frequency at another point in time. And this can be seen in the image right there, where one side of the image seems to show a different curve than the other. Although the same sentences are being said, they have different curves because one is being said in a happy or upbeat tone versus the other one is being said in a more depressing or sad tone. And you can see there's clearly a difference in the pitch contour. So the challenge here for speech synthesis is to create that natural pitch contour when technology is being used. So one methodology for this is the words to phoneme methodology. And a phoneme is basically sounds that make up a word, such as like cat, for example, is made up of the phonemes cat, at. So this methodology can be used. However, it is kind of tough to be used because some words are irregular and can also be pronounced in different ways. For example, if you take READ, which is read or read, this is an example where words to phoneme could be a bit difficult. And an example of this issue is like in Siri. Siri has a more robotic voice without like too much pitch contour and also can pronounce things incorrectly. Okay, so now I'll be talking about prosody. Prosody is the intonation and rhythm of speech, which can reveal certain details about a segment of speech. So there's different kinds of prosody, and one kind of prosody is emotional intent. And prosody can reveal a lot about what is being said, such as, is it a question? Is it a statement? Is it a command? So this requires a certain level of emotional understanding of words and how some words might carry more of a weight or more of a pitch and can be spoken in a different tone than other words. And of course, human speech contains pauses as well as tonal inflections, and this can also be just due to like human breathing. That creates a natural pause or a natural inflection in human speech, and this can be very hard to replicate. So now I will be talking about intent. And intent is the meaning and purpose of speech. Emotional intent can be the hardest to use within speech synthesis, and datasets containing definitions and possible intent can still be confusing, and there might not be a lot of storage space either for these datasets or trained models, and that can actually cause an engine to slow down, and that would actually worsen the speech synthesis process. And also, a lot of intent is sometimes communicated with nonverbal cues in addition to speech. This might include, body language, eye movement, and this would be very, very hard to replicate. Now I'll be talking more about database size. Speech synthesizers have voice database or an inventory of speech, and this ties back into unit selection, especially when creating a more personal voice. Unit selection is creating new speech that doesn't exist in a dataset or model using a subword unit that does exist. And the challenge here is that sometimes it can be very tough to have a larger database or a larger dataset because this can easily slow down the speech synthesizing process. And also, depending on the hardware that the synthesizer is running on, this can definitely be an issue if the hardware just does not have the memory or the space for this.
I am Ariel Sanchez, and I'm going to be talking about the solutions that we currently have for speech synthesis challenges, such as speech contour in its natural state, prosody and intonation, as well as database. Pitch contour stylization, in general, it's a powerful tool for designing prosodic models in speech synthesis. Stylization is frequently thought of as a method of reducing the amount of information contained in the basic frequency trace in order to maintain only those sections of the pitch curve that have a linguistic role in voice transmission and are thus required for prosody synthesis. There are multiple methods for the efficacy improvement of natural speech contour. Automatic stylization outputs the utterance series of auditory pitch events, such as static tones, dynamic tones, complicated dynamic tones. Automatic stylization of pitch contours are based in tonal perception, produces a simplified contour that is hardly distinguishable from the original, and it could be even better than the original. The stylization obtained with the manual interactive procedure known as closed copy stylization. Closed copy stylization, it's a manual method that involves resynthesis of the stylized contour and auditory comparison with the original to achieve a straight line approximation of the pitch contour. That's where manual straight line stylization comes in, which is a procedure in which the observed pitch contour is replaced by a less complex contour, having the form of a concatenation of straight lines. It is based on the hypothesis that unnecessary details of the natural melodic curves can be ruled out without any perceptual change. No structural assumption has been made up to know about the nature of such details, but it's extremely useful. A good approach to tackle prosody and intonation is the basic point of differentiating two types of emotion. emotional prosody, and the second one being the emotive intonation. So it is necessary to think that to have some emotion classification as a basis is really relevant. Complex emotions are a characteristic for the emotive utterance semantics. That is why it is necessary to know phonetics and how prosodic correlates of simple and complex emotions. Emotional prosody is the zone of expressing uncontrolled and unconscious general emotional state of a person. The sphere of application of the emotional prosody is the text. Emotive intonation is the zone of expressing emotions that can compound the emotive meanings of different language units. The sphere of application of the emotive prosody lies within the utterance field, primarily emotive utterances, emotive speech acts, for example, with the emotions expressing it as its predominating force. Anyway, we realize that there is no evident demarcation between them. A good example is the intonation of emotive and emotionally colored utterances expressing the same exact emotion. Emotive intonation has the language specifically express the concrete emotive meanings. It's very important to define the specificity of these emotions as if they are controlled and conscious ones. From the properly linguistic point of view, the emotion expressing will be conscious if it forms the dominating communication aim of the speaker. These types of emotions are necessary to compare many languages, but this problem can be solved only if the data is comparable. It is important for the phoneticians who make their research on different languages to base on the same principles, being extremely relevant when designing speech synthesis solutions to come up with the best algorithm possible. An example could be the Mary open source emotional text-to-speech software. Mary is a multilingual, multi-platform speech synthesis system written in Java. Mary can synthesize emotionally expressive speech using diphone voices. Using the speech synthesis markup language, as they call it, Mary can control the intonation generated for emotional voices from markup and can change the shape of the intonation curve. Related to the database issues, we solved the problem in two procedures. First, by representing each role with the Gaussian mixture models, or GMM. All speech data is partitioned into a number of voice style clusters with the criteria that maximizes the likelihood of all utterances with respect to role speaker models. The remaining solution, or the next step, includes pruning in terms of both acoustic and prosodic measures, followed to purify the clusters to identify a set of representative voice styles that could be in an audiobook, for example, and to assign to each voice style with the appropriate utterances, which should reflect the characteristics of the corresponding style. First, roles are represented by GMMs, and all speech data are partitioned into a number of voice style clusters As a result, we could synthesize speech reflecting the characteristics of these voice styles by synthesizing from the corresponding corpora. In using speaker verification, not all utterances inside the same cluster sound familiar enough to each other, since some utterances sound far from all clusters and have to be assigned to the nearest group. something similar than what happens in k-nearest neighbors in machine learning. Thus, we've verified the utterance in terms of both acoustic and prosodic measures to purify these stylistic databases. Pruning with prosodic measures, GMM-based role models do not account for temporal information of speech waveforms and lack the ability to capture speakers' prosodic characteristics. Therefore, we continue to employ prosodic confidence measures to remove the utterances that sound rather different in prosody from the voice normal speaking way. We need to measure the deviation of an utterance from its expected prosody contour that is predicted by prosodic decision trees with the sentence transcription as an input. So it's extremely tied to machine learning, related to decision trees. With the upcoming development of Internet of Things, more and more devices need less and less hardware storage as long as they connect to a web-based database. And with the improved internet latency and query response through the last decade, we don't see as often the issues relying the hardware needed for the speech synthesis solutions that we currently have for speech synthesis.
Future of speech synthesis. With the increasing inventions and developments in speech synthesis, there have been various challenges that are previously discussed by Vinita. The solutions to them, as mentioned by Ariel, allow these developments to be implemented in real time, and developers have been trying to optimize the algorithms for speech synthesis as its applications have evolved to become a crucial part of our daily lives. The future of speech synthesis will focus mainly on three aspects. The first one is using neural networks to generate speech. Some of the speech synthesis methods often result in robotic or inauthentic voices. To resolve that, neural network algorithms are being implemented so that the user can have a comprehensive conversation with the robots. The second focus is towards generating emotive voice experience. This will include generating a dynamic voice that can deliver a variety of emotions according to the user's mood to deliver optimal engagement in various languages and dialects. The third focus is towards voice experience. Giant tech companies are highly focused on this right now, since voice as a channel is powerful, convenient, lightweight, and a part of everyday life. Without a strong voice experience, all the benefits of voice as a channel would disappear. Much of the focus in coming years will center upon enhancing voice quality and ensuring voice as a channel is optimized. To do this, neural networks will play an integral role. It will be interesting and exciting to see the forthcoming developments in the field of speech synthesis and the flexibilities it will offer to humans in the coming years. Thank you.